warahmatullahi wabarakatuh. So we start with our lecture, or we continue our lecture for week 1, lecture number 4. So this one we want to describe the three quantities of radiation, describe the interaction of ionizing radiation with matter. Okay, so the quantity is the karma, absorbed dose, and the exposure. Okay, so we define the three non-stochastic quantities useful to describing the interaction of the radiation field with matter, and also the excitation value of the for the infinitesimal sphere at the point of interest. So the quantities are, as I said, the karma K. So this one describing the first step in energy dissipation by indirectly ionizing radiation, that is energy transfer to charged particle. Okay, so it will excite the radiation will excite the sum of particle, and that particle will do the rest. Okay, so to excite that particle, you need to transfer the energy from this radiation. Okay, the next one is the absorbed dose. Okay, the energy imparted to matter by all kind of ionizing radiation, but delivered by the charged particle. Okay, so this one you can see that if we have a lot of radiation source, okay, so all we count all, and then we refer to this charged particle. So what are the energy that the charged particle get? Okay, and then next is the exposure. Okay, so I describe the alpha X-ray or gamma ray field in terms of the ability to ionize the air. Okay, so this one X and Y. So the energy, how much energy that it can ionize the volume. Okay, so the definition for these three quantities from this International Commission on Radiation Unit, ICRU. So ICRU 1988, 1988 and 2011. Okay, so energy transferred by indirectly ionizing radiation lead to the definition of karma. Okay, so this radiation, so we excite this charged particle, and then charged particle will get the energy. Okay, energy imparted by ionizing radiation, so lead to the definition of absorbed dose. Okay, so this one is directly ionizing radiation, so this is directly ionizing radiation. And energy carried by neutrinos is ignored, so we are not going to put even though this is F, but it will not be counted in these quantities. Okay, because neutrino are elementary particle having no electric charge and particularly zero mass, and they have an small cross section for interacting with matter. Okay, so you will not interact with this matter. Okay, so for this part, lecture number 4, so we only focus on karma. Okay, so again, karma is the expectation value of the energy transferred to charged particle per unit mass at a point of interest, including relative loss energy, but excluding energy passed from one charged particle to another. Okay, so meaning that here uh, we have this radiation. So radiation pass the energy to the charged particle, and the particle will do the rest of the work. Okay, so for example here it is killing the cancer. Okay, so how how much energy it get from each radiation, so to kill the cancer. Okay, so here the value or the calculation for the karma, or the formula for the karma, there is a lot of equation, but here is one of them. So K at point of interest P in a volume V. Okay, so we can calculate kerma using this d bar epsilon tr over dm. So where ETRE is the expression value of the energy transferred in the finite volume V during some interval. So we count the energy transferred, for example, for 10 seconds, 20 seconds. So how much energy will be transferred from the radiation to the cell. Okay, and then the expression value of the energy transferred for the infinitesimal volume dV at the internal point P. Okay, so this one is the energy transferred at the specific volume and point. Okay, and dm is the mass in that volume. Okay, so the term energy transferred, so the energy transferred is in the volume V is equal to var epsilon tr over r in u minus r out u non-radiative plus q. So where this one r in u is the radiant energy of uncharged particle entering V, r out u and r radiant energy of uncharged particle leaving V. Okay, not from radiative loss. And EQ is the energy derived, net energy derived from the rest mass in V when M approaching in, the mass approaching the E positive and E approaching mass equal negative. Okay, so these are the net energy. So R out, so this one does not include relative loss of kinetic energy by charged particle, the Bremsstrahlung or in-flight annihilation. So we do not count this Bremsstrahlung and in-flight annihilation. Okay, so and the radiant energy R is the energy of particle emitted, transferred or received, excluding the rest mass energy. Okay, so we have this one R and so the unit for this kerma is equal to 1 gray or equal to 1 joule per kilogram or 10 to the power of 2 radians or 10 to the power of 4 ERG over G. So these are the kerma. Okay, so next we see the relation of kerma to energy fluence of the photon. So we have the photon. This is just like the wave-like energy. Okay, and when we see later the neutron, the particle type of energy. Okay, so for monoenergetic photon, so meaning that the photon with only one energy, one value of energy, and medium of atomic number Z of the matter at P. So if you see that only one atom, not one atom, one type of atom at P. So relation is through the mass energy transfer coefficient. So K, here we say that K equal to this equation, but kerma can also be calculated using this energy fluence. So psi mu tr over rho E and Z. E fixed, Z fixed. Okay, so where mu tr is the linear energy transfer coefficient, rho is the density, and psi is the energy fluence. So this one for energy spectrum of photon energy. So for photon with different type of energy or very different value of energy, E1, E2, En, or whatever. So psi dot E, so the kerma is equal to K integration from 0 to E max of this equation. So we can get again this mu tr over rho is the mass energy transfer coefficient, m squared per kilogram. Psi dot E, the division of photon energy fluence. Okay, so depend on the each energy E1, E2, E3 until En. So these are the coefficient, mass energy transfer coefficient. Okay, so from appendix D3 from our textbook. So we can use for this hydrogen, carbon, nitrogen, oxygen. So these are just example. Okay, so if we have a lot, another one. But as we can see, if we see the the molecule or the cell in our body is contained from hydrogen, carbon, nitrogen, oxygen. So this energy, radiation energy will affect this hydrogen, carbon, nitrogen, and oxygen in the cell. Okay, so these are thermal relation to fluence of neutron. So these are neutron. The previous one is photon. So these are neutron particle. Okay, so neutron field is described in terms of fluence rather than energy fluence. Okay, so how many particle or the flux of particle coming to the point. Okay, so the Kerma factor for tabulated for neutron instead of the mass energy transfer coefficient. So for the neutron, so we do or we assume radiation as a particle. Okay, so we use the Kerma factor. Okay, so if we assume the radiation as a wave light, so we use the energy fluence. Okay, so this one or the mass energy transfer. Okay, so here we see that these are the Kerma factor. Okay, again for monoenergetic neutron, there's only one value of energy. So the Kerma is equal to P times Fnez. So P equal to the influence of monoenergetic neutron of energy E, and F and Ez is the Kerma factor for those neutrons in the irradiated material Z. Okay, so depend on this Z. And for neutron having an energy spectrum of P dot E of particle fluence, so again we can just integrate the sum from this equation. Okay, so the fluence of neutron of energy E1, E2, E3, E4, E5, E6, En, and F and Ez is the Kerma factor value. Okay, for each energy E1, E2, E3, E4. So these are the neutron Kerma factor again for hydrogen, lithium 6, lithium 7, boron, carbon, nitrogen, oxygen. Okay, so we have this, and these are the energy. So these are the Kerma factor for this energy. Okay, so we see the component of Kerma. Okay, so the energy received by the charged particle may be spent in two ways: collision, interaction. Okay, so the charged particle will collide or do the collision or hit the target. So Coulomb force interaction with before it can hit the target, it may face the Coulomb force interaction. Okay, so Coulomb force interaction with atomic electron of the surrounding material within the local distribution of energy as ionization and excitation in or near the electron track. Okay, so you can excite if it exceeds this Coulomb force interaction, so it can kick out this electron. Okay, so then that material will be ionized. Okay, so radiative interaction with Coulomb force or field of atomic nuclei in which X-ray, photon, bremsstrahlung are emitted as the electron disappear. Okay, so this one it cannot go to this because this energy is less than the Coulomb force. Okay, so it just do the interaction, and this particle move slowly after doing this Coulomb interaction with Coulomb force. Okay, so for Kerma, for photon, or for the wave-like radiation, may be subdivided into two component, collision. Okay, this collision, this one, collide with the atom and or the electron and radiative during the Bremsstrahlung or position annihilation. Okay, so when Kerma is to the neutron particle, heavy particle, charged particle are much heavier, so it and the energy is greater than this Coulomb force interaction, so it can hit the electron and take out the electron. So K equal to Kc without the K. Okay, so the net energy transferred from the particle to the uh, molecule or for the atom, so equal to this equation. This one is var epsilon Tr, not var epsilon time Tr. Okay, so where R is the radiant energy emitted as radiance lost by the charged particle. So the kinetic energy, say E Tr, these are net, these are Tr transferred. So Kc with which Kerma without radiative loss is dEtr. So this equation or this equation divided by dm. Okay, or differentiate with respect to dm. So the expression value of the net energy transferred in the finite volume during some time interval, and dm is the mass in dV. Okay. Okay, so the collision Kerma is the expression value of the net energy transferred to charged particle per unit mass at the point of interest, explain both of relative loss energy and energy passed from one charged particle to another charge. Okay, so this one minus this one, K dEtr net over dm. Okay, and the mass energy absorption coefficient. Okay, so how much it absorbs the energy for each radiation or for each radiation incoming radiation is equal to for monoenergetic photon, again these are for wave-like radiation, equal to Kc equal to psi mu En over rho Ez. Okay, so depend on the material present along particle track before reaching point P. Okay, so maknanya particle tu sebelum dia sampai kepada sel yang tertentu, dia akan jumpa macam-macam sel, macam-macam atom. Okay, so each atom will decrease its energy. Okay, so depend on. Okay. So here there's coefficient for this for low Z material and low energy relative loss are small. So here this energy. So gamma ray energy, so small gamma ray energy or low gamma ray energy, so you can see that the energy loss is nearly 0, z equals 6, 29, 82, 10 megaelectron volt. You can see that the energy the coefficient is 3.5, 13.3, 26. Okay, so here you can see that these are collision coefficient. Okay, so the last one, so the Kerma rate, okay, the energy transferred at a point P at n time t, K dot equal to dk over dt, dt over dt, d var epsilon Tr over dm. So the Kerma occurring between the selected time limit to T0 and T1 will then K T0 T1 the just integration of this the Kerma rate, and for constant kerma. So we just take k dot times t minus 1 t1 minus t naught. Okay, so these are just like our calculus. Okay, the area under the graph. Okay, so that is for kerma. So for next lecture we are going to see the absorbed dose and the exposure. Thank you.